Welcome to my second series of lectures on tensors. In the first lecture series, I had talked about tensors under linear coordinate transformations. And near the very end of that series, I had focused on how these results would be adapted if we were talking about a more general coordinate transformation. In this series, I am going to focus on tensors and of course scalars and vectors and similar objects under a coordinate transformation which is general, not just a linear one. This would be of interest to people studying topics where general coordinate transformations are actually symmetries. The most obvious example of this being the topic of general relativity. Although that is not the only place where general coordinate transformations are useful, it does happen to be one of the major places where they find application. Let me also state that I am not going to use the more elegant and beautiful language of differential geometry in these lectures. I actually have a separate series of lectures which is being sort of constructed slowly at this moment on that topic. What I am going to do is use components of tensors, scalars and vectors, how they transform under general coordinates and so on, the so-called index gymnastics, which is actually very useful for practical applications in this series. So to begin with, let us do a recapitulation. I am calling this a recapitulation for those of you who have already seen my series number 1 or who have actually studied the topic of scalars, vectors, tensors under linear coordinate transformations, say in special relativity. For those of you who have no such exposure, I am going to make this recapitulation a bit detailed so that you can follow the rest of the series without necessarily having to look up the whole thing all over again. Let us begin with how we denote our coordinates. If we have a d-dimensional space, a point in that space will be denoted by d coordinates, d in real numbers, and typically they will be written as xi, where I runs from 1, 2 all the way up to d. Now, depending on which topic you are studying, especially if you are studying topics involving space-time in which there is one time dimension which has to be separated from the other spatial dimensions, you might have some other range over which the indices run. For example, typically in three-dimensional space-time, you would have 0, 1, 2. And in four-dimensional space-time, you would have 0, 1, 2 and 3, which is our standard 3 space and 1 time dimension that we live in, at least we think we live in. Now this x upper I simply stands for x1, x2 all the way up to xd. And under a coordinate transformation, they change to new coordinates, say x prime 1, x prime 2 up to x prime d. And physicists are usually a bit sloppy with their notation as far as mathematics is concerned. And it's not a surprise that physicists often use xi to stand for either the ith component or ith coordinate in this case, or they use xi to stand for the whole set of components. Usually it is clear from the context what is being meant, so we will not really labor too much on that point here. Now, for a linear transformation of coordinates, xi becomes x prime I. So x prime 1, x prime 2 up to x prime d, and they depend linearly on the original x's. So you get the new x's, the x primes, by taking the old x's, multiplying them by some real numbers and adding them together. And that thing is written here in the form lambda ij xj. Here we are using the Einstein summation convention, where the idea is that if the same index appears twice, once downstairs, that is as a subscript, and again upstairs as a superscript, then you will actually imply a sum over that particular index. So J here takes all its allowed values, 1, 2 all the way up to D, or 0, 1, 2 all the way up to D minus 1 as the case may be, and assuming it's 1, 2 all the way up to D, this really means lambda I1 x1 plus lambda I2 x2 all the way up to lambda ID xd. Note that here J is what is called a dummy index. Whether you write this as J or K or L or any other index notation that you want, that doesn't really matter, because if it is going to be repeated, then its actual identity as an alphabet disappears. You just have to sum up over all possible values that the index can take. The one value it's not allowed to take is I, because then you would be confusing it with the other index which is here. This is an example of a free index. Here it does make sense to say that I is 1 or 2 or D. Some specific value of I can be talked about. And the standard rule here is that the free indices have to match on both sides of an equation, and they have to be in the same position. Dummy indices have to be summed over, and they are always in an upstairs downstairs fashion. Now, we can also write this whole equation more compactly. Any linear equation can be written compactly using matrices. So if we think of the column vector x as a d-dimensional column vector with x1, x2 all the way up to xd as its components, and x prime, a similar thing with x prime 1, x prime 2 all the way up to x prime d, then this equation can simply be written as x prime. The column vector is L the matrix acting on X the column vector. And as you can see, this notation and this notation are very consistent. When you multiply a matrix by a column vector, or apply a matrix on a column vector to be more precise, then you actually sum up over the column index of the matrix with the only index which the column vector has. You put them together and add them up. So here it's obvious that L, this matrix, has as its ith row jth column element this number lambda ij. So lambda ij is the element in the ith row and the jth column of the matrix L. So if we were using standard old matrix notation, we might write Lij with I and j both downstairs. What we choose to write is lambda with I upstairs, j downstairs. Now this upstairs downstairs thing going from the top left to the bottom right, as this arrow indicates, is what you use for the coefficients which tell you how coordinates transform. Now, of course, the reason why you put the I upstairs and the j downstairs is to be consistent with the rule that we just said. Free indices have to be in the same position on both sides. So, since you have I upstairs here, you have I upstairs here, and the dummy indices have to be summed up, but they have to be downstairs and the other has to be upstairs. X's are always written with upstairs indices, and so x upper j has to come with a lower j on lambda. So that sort of explains why you have this particular notation. It's also important to note that you will see a distinctly different lambda, lambda ij, where the index positions are different. Here the indices go from bottom left to top right, in the opposite diagonal direction. And you will soon see why you have these two different kinds of ways of writing indices on lambda. But let me warn you right now that these elements, although they are related to these elements, are not the same as the matrix elements of Lij. They are the ith row jth column elements of some matrix, of course, but that matrix is not L. We will soon see what that is. Let us now move on to what kind of objects can we have under a linear coordinate transformations. The simplest kind of objects we can have are scalars. These are described by a single number, which is what we mean by a one component object, and these numbers are invariant. They do not change when you change your coordinates. So scalars are as simple as they can be, and the simple rule for scalar transformation is phi goes to phi prime, which is equal to phi. Now vectors. These are essentially the same kind of objects that we learned about in high school. And the basic idea is that when you want to define it in more advanced language, you would say that a vector in a d-dimensional space would be described by d numbers, d real numbers, d components, which transform in exactly the same way as the coordinates do. So when the coordinates xi goes over to x prime I given by lambda ij xj, the d components of the vector v, v1, v2 all the way up to vd, they change in the following manner. vi becomes v prime I, which is equal to lambda ij vj. Note that the coefficients lambda ij here, the coefficient in front of vj in the expression for v prime I is exactly the same as the coefficient in front of xj in the expansion for x prime I. So exactly the same coefficients as the coordinates. And it's obvious that if I now put v1, v2, vd in the form of a column vector and call that v, and have a similar thing for v prime and so on, v prime will be related to v by simply the matrix L, the same matrix as the coordinates acting on v. Now we come to a new kind of object which you may not have studied in high school. Well, you definitely did not study it in high school. Some of you have studied it in college. These are called covectors. And covectors really are nothing but linear maps from vectors to real numbers. Now, I can go in a lot of detail here, but because this is essentially a recap, I'm going through this a bit quickly. Covectors are described like vectors by d real numbers, the d components of a covector. And for a covector w, you write the components as wi, w1, w2, w3 and so on. But this time you use the index downstairs. So you write the index as a suffix and not a superfix. Vectors, like coordinates, have indices which are upstairs. Covectors have indices which are downstairs. And indeed, this is the reason why we have this upstairs-downstairs mix of positions for indices. We need a way to distinguish between vectors and covectors. And because both of them have exactly one index which runs from 1 to d. If you are using the index notation, the only real way in which you can do that is by placing the index in a different place. Now, the reason why you want to place it in a different place is simply because the transformation rule for covectors, indeed the reason why you call it a different kind of object in the first place, is that the transformation rule for covectors is different than the transformation rule for vectors. So under the same coordinate transformation, xi going over to x prime I equals lambda ij xj, wi goes over to w prime I, which is given by something which looks very similar but is actually different. Note the different positioning of the indices, and as we have already said before, these lambdas, the numbers, are components of an entirely different matrix. Well, not entirely different, a related matrix, and we will soon see what the relation is. So w prime I is lambda ij wj. Once again notice that the rules for placement of indices and the dummy index summation are all obeyed here. You have a downstairs index I on the left, so you must have a downstairs index on the right hand side for I, and w must have a downstairs index j, so the other index in lambda must be upstairs, so that our summation convention rule can work. So let's call the matrix whose ijth element is lambda ij L bar. L bar's ijth element is this lambda ij. For future convenience, we are going to call these the vector transformation coefficients and these the covector transformation coefficients, if we have to distinguish them. Obviously, the transformation rule for the covector as written in the column vector form would be W prime equals L bar W. Now, the reason why we actually have a different transformation rule for covectors as opposed to vectors, the reason why we have covectors in the first place, is that what we want to do is ensure that the covector acting on the vector produces a number which is a scalar, an invariant, or you can also think of this as a vector acting on the covector. Either way, the number that is formed when you take v1, v2, v3, vd, the vector, and w1, w2, w3, wd, the covector, together and form a scalar out of it, make one act on the other, if use this expression vi, wi, where the positioning of the indices tell you that I is summed over. So this really means v1 w1 plus v2 w2 all the way up to vd wd. That's what this expression means. This is of course a number. The thing that we demand and what makes w a covector is that this number is invariant under a coordinate transformation. What that means is when we change the coordinates and we get w primes and w v primes, w prime I v prime I must be the same as w I v I, and just because we can, we have written the index here on the right hand side differently. Remember, wj, vj, wi, vi, all of them mean the same thing. w1, v1 plus w2, v2 all the way up to wd, vd. Let us now work out the relationship between the two different kinds of lambdas that we have written so far, the relationship between the matrix L and the matrix L bar, by exploiting this particular demand. Note that w prime I is nothing but lambda I upper k wk. This is a covector transformation coefficient at work here, whereas v prime I is nothing but lambda il vl. This of course is a vector transformation coefficient. Of course, the sum over k and the sum over L is implied on the left hand side, and this must be the same as wj vj. I have deliberately written this as k and this index as L in order that we do not mix up the dummy indices. We are already using j on the right hand side, so we avoided using j here, and once I have chosen to write this as k, I have to choose some other letter for this particular index. Now, this entity is nothing but a number, so I can of course pull it in front. So I get lambda ik, lambda il, wk vl. Now you have wk vl, the original w and v components on the left hand side. We have wj vj here, but we can also write this as wk vl by putting in the coefficients delta kl in front. Delta kl, remember, is nothing but the Kronecker delta symbol, where the number that this stands for is 1 if k and l are equal and is 0 when k and l are unequal. And this ensures that when you do a sum over, say, L, all the L's must become k in the expression, because otherwise the coefficient would simply be 0. So we will get wk vk, which is of course the same as wj vj. Now, since this has to be correct, no matter what values of W1, W2 up to WD or V1, V2, VD you use, it's easy to see that the coefficients in front in the two cases must match. So lambda I K, lambda IL must be delta KL. Note that so far we have been keeping the indices placed properly. The one on the left is of course the row index, one on the right is the column index, irrespective of whether it's downstairs or upstairs. These are of course row and column indices of different matrices. This one is for L bar, this is for L. For deltas, we will often write delta KL with K and L right on top of each other because Kronecker delta is symmetric. It doesn't really matter which one is the first one, which one is the second index. Now, if you want to rewrite this in the matrix language, this simply means that the ikth element of L bar times ilth element of L, summed over I of course, is IKL, where I is the identity matrix. Of course, the KLth element of the identity matrix is nothing but delta KL. Now, this looks like a matrix multiplication, but it is not. In a matrix multiplication, the column index of the first matrix and the row index of the second matrix are matched and they are multiplied together and then summed over. It's the I index being used here, but I is the row index of the first matrix. But of course, it will be the column index of L bar transpose. So this is L bar transpose KI LIL, which is IKL. And what that means is you take the transpose of L bar and multiply that by L and you do get the identity. And so it follows that L bar is nothing but the transpose of L inverse or the inverse of L transpose, whichever way you look at it. So the two matrices, one which tell you how vectors transform and the other which tells you how covectors transform, are related to each other. And they are related in a way which ensures that when you put a vector and a covector together, when you make one act on the other, you end up with an invariant. And the relationship is simply this: L bar is L transpose inverse. Now, we can sum up by saying, while under a linear coordinate transformation x goes to x prime, which is Lx, vectors transform as v goes to v prime, which is Lv, the same transformation as the coordinates. Covectors transform as w goes to w prime, given by L transpose inverse w. Indeed, the covector transformation rule would look a bit cleaner if we were to sort of understand that since covectors act on vectors to give you numbers, a proper representation for them would really not be as column vectors, but rather as row vectors. Remember, even in matrix theory, a row vector, a d-dimensional row vector acting on a d-dimensional column vector, is what gives you a number. So instead of w, the column vector, you could have used w transpose. Let's call that w tilde. And if we were to use that to represent our covector, then the transformation rule becomes a lot more meaningful. W tilde becomes W tilde prime, and notice the W tilde prime is nothing but W prime transpose or L transpose inverse W's transpose. And using the standard rule that when you transpose a product of matrices, each matrix gets transposed but in the reverse order, you get W transpose, that is W tilde, into L transpose inverse transpose, that is L inverse. So W tilde transforms to W tilde L inverse. This actually makes it very clear that vectors and covectors actually transform oppositely. Vectors transform like coordinates, covectors do just the opposite. Now we come to tensors. Now just like we could talk about covectors as maps which act on vectors linearly, or equivalently talk about vectors as maps which act on covectors linearly, a tensor is really a generalization. It's a map which acts on some vectors, also possibly some covectors, and returns a scalar, an invariant number. And what's important is that it does so multilinearly. That is, it has to be linear in each and every one of its arguments. So to understand what is going on here, let's take a look at one example. I'm going to take a pretty complicated example which may be a bit scary, but don't worry, usually we will not really need to worry about tensors which are actually this complicated. And you will soon see even such complicated tensors are really not that difficult to understand. Let's say we have for our tensor a multilinear map which takes in 2 vectors and 4 covectors. And I could have also, of course, put the covector arguments at the beginning and the vector arguments at the back or than the reverse. But let's just say in our case, the first 2 arguments happen to be covectors. The next 2 happen to be vectors. And the final 2, again covectors. As you must have noticed, I have written vectors without tildes and covectors with tildes. Now that we are talking about the entire objects, we can't really distinguish between them by the positioning of the indices. When you talk about them component by component, of course, indices help tell you whether you're talking about a covector or a vector. Here, you have no such option, so I'm using tildes for covectors and no sign for vectors. Now notice that each one of these actually are written in terms of some basis vectors, and that's why we have components. So when you say P has components P1, P2, P3, etc. up to Pd, what you really mean is the vector P is P1, E1 plus P2, E2 all the way up to Pd, Ed, where E1, E2 up to Ed are D vectors which form the basis of a vector space. Covectors also form a vector space, a different vector space with a different basis. Let's say the basis vectors there are F1, F2, F3 and so on. So our V, for example, the V tilde will be written as V1. Note that now that we are using indices, we will no longer have to write the tilde. So V1, F1 plus V2, F2, Vd, Fd, and of course, the reason why we have placed the indices in this way is to ensure that we can actually use our summation convention and write this as Pi, Ei, and this as Vj, Fj. Now, using the fact that T is a multilinear map, we can actually rewrite this result of T acting on this bunch of arguments in the following fashion. First, let us write down each of the arguments in this form. So V tilde will become Vi, Fi. W tilde again is a covector, has components and is expressed in the same basis as V tilde is. So Wj, Fj. P and Q are vectors, so they use the EIs as basis vectors. So I will write this as Pk, Ek. Note, of course, that I am using different dummy indices just so that we don't confuse one with the other. Q, L, E, L. Then we have S, M, Fm, and T, N, Fn. Now comes the important part. Each of these arguments have been written as a linear combination. And because of multilinearity, each of these coefficients can be pulled out from this T. And you can rewrite the whole thing as Vi, Wj, Pk, Ql, Sm, Tn. These are just numbers which have been pulled out. And what you are left with is T acting on Fi, Fj, Ek, El, Fm, Fn. So once you have chosen a basis on your vector space and covector space, you can actually write the action of a tensor on any set of vectors and covectors which may be its arguments by essentially telling me what T does to this combination of basis covectors and vectors, and of course supplementing that with the actual components which the vectors or the covectors as arguments have. So this simply becomes Vi, Wj, Pk, Ql, Sm, Tn. And here, this thing after all is a single number. Of course, when I say single number, I mean one number for each value of I, j, k, l, mn. So if each of these indices can take d values, these are d to the 6 numbers in all, and I will write this number with the same kernel letter T and just use these indices and put them in the right position. So note that this notation here has a very big similarity with the Vi, Wi that we used while ago. There also you had an I upstairs and an I downstairs, you got a number. Here you have Ij upstairs, Ij downstairs, Kl upstairs, Kl downstairs, Mn upstairs and downstairs. Each of them are being added up over. So in fact the right hand side here actually has d to the 6 terms, and the important thing is that role which the tensor itself plays can be summed up in these numbers. So if you know the d to the 6 numbers T, I, j, k, l, mn, you know this particular tensor. Of course, the fact that this tensor has d to the 6 components depends on the fact that it actually has 6 arguments, 4 covectors and 2 vectors. If you had, say, only 2 arguments, then you would have had only 2 indices and so on. So, these components tell you all that you need to know about the tensor. But of course, these components depend on a particular choice of coordinates, because your basis vectors and the basis covectors are of course related to the choice of coordinates that you are using. So what happens when you change coordinates? Now let me first tell you the rule that you apply here, and the rule actually is pretty straightforward, and it essentially looks like this. Remember, with vectors the transformation rule was Vi goes to V prime I equals lambda I j Vj. Here the vector transformation rule, upper index here I, upper index here I, lower index j, contracting with or getting summed up over this upper index j. With covectors you had W prime I equals lambda I j Wj. Now the transformation rule for T, which has 6 indices here in our example, will be T prime I j k l m n equals, and now I will have several dummy indices to worry about. In fact, one dummy index for each of these free indices on this side, and rather than worry about running into the same index twice by accident, I will choose the dummy indices from a different part of the alphabet. Let's say I will start from the beginning. So with lambda I will put in a A. Note that this is an upstairs index, and the rule is if you have an upstairs index on this side, you have a vector transformation coefficient. Similarly with J, you will have a B. With K on the other hand, that's a downstairs index, you have a covector transformation coefficient Kc, Ld, again same, covector transformation coefficient, then two vector transformation coefficients M, E and lambda and F. I hope you will not confuse this index E with the E1, E2, E3 for the basis. Times the A, B, C, D, E, F component of the tensor T in the original coordinates. So, just like you can figure out the new components of a vector or a covector using the vector and covector transformation coefficients, you can also work it out for a tensor. The only difference is you will have more such coefficients multiplied together. And of course, here you are summing up over 6 dummy indices A, B, C, D, E and F. And that means that you are actually carrying out d to the power 6 sums all at once on the right hand side. Now d to the 6 for any reasonable d could be a huge number, but you don't really have to worry about that. It is very rare that you have to explicitly carry out the summation. Much of the calculations can be done using basic properties, and let me illustrate one of them. I have claimed that this is a transformation rule for tensors. But how do we know that we have actually hit upon the correct transformation rule? The important point is, tensor components must transform in such a way that the multilinear structure of the tensor map must prevail, and ultimately a tensor acting on the appropriate number of vectors and covectors must give you a scalar. In other words, this expression must give you a scalar. So let's see whether that's true. So if you were to transform coordinates, what would happen to this expression? It will become V prime I, W prime J, P prime K, Q prime L, S prime M, T prime N, T prime I, J, K, M, N. Now, V prime I is of course lambda I. Well, I cannot use ABCD once again because I will use ABCD for the transformation rules for this. So, let's move on to P, Q, R, S and so on. Lambda IP, VP, lambda J, Q, WQ. Then we have vectors transforming, so it will be lambda K, R, P, R, lambda L, S, Q, S, well, PQ, RL, PQ, RS, TU. So, I am now actually revising my alphabets. Lambda T, M, SM. Sorry, this is completely wrong. Lambda M, T, S, T. Now I am really running into trouble here because T is also the name that I have given to my vector. I hope nobody will confuse the name of the vector with the index T here. Anyway, let's press on, and then you have lambda N, U. Okay, let's just do one thing. Instead of calling this T, I will call this U. Once again, remember that I can call the dummy index whatever I want, and I don't really want to get into a source of confusion. This is lengthy enough, not difficult, but lengthy enough as it is, times this thing, which is nothing but this whole expression. So let me just put that in along with it. So this is what the transformed value is. Is it the same as the original value? Now how do I check? Now notice you have lambda IP, lambda IA. This is actually the pith element of L inverse times the iath element of L. So, it's actually the pAth element of the identity, delta PA. So, these two together give you delta PA, this one and this one. So, if I get rid of these two, I'll get delta PA. Similarly, you're summing up over J between this, and this gives you delta QB. Of course, you have VP, WQ. When you take this, lambda KR and lambda KC, again, this time you can think of either putting the lambda KC ahead of the lambda KR and then again see that it really gives you delta CR directly. Or you can think of this as L's KR's element multiplied by L transpose inverse as KCth element. So this is really L transpose inverse multiplied together and so on. But I think you get the gist. So this will be delta CR, PR, delta D, S here when you sum up over the L. Note that one thing we are doing very carefully is keeping the upstairs downstairs relationship for the free indices intact. Lambda mu, lambda me. Again, here you have a covector transformation coefficient, here you have a vector transformation coefficient. When you add up over m, it simply gives you delta UE. These two together will give you delta VF. Of course, delta DS came with QS. Here you had SU. Here you had TB. And then you had this T, A, B, C, D, EF. But now notice the job of this delta, say delta PA, when you sum up over P, would be to make all the P's equal to A. So this becomes VA. Similarly, this becomes WB. The P becomes PC. QD. S. So S, E, T, F, T, A, B, C, D, E, F. So notice this is exactly what the value was before. This is a transformed value and the two are the same. So the fact that we have chosen our transformation rule for tensor components by putting in a vector transformation coefficient for each upstairs index on the component of a tensor and a covector transformation coefficient for each downstairs index actually works out. It does ensure that the tensor seen as a multilinear map acting on its arguments really gives you a scalar when they act on the right kind of arguments. Now, I do realize that seeing all these coefficients jumping around and all these deltas, the summations, this may look a bit too complicated to some of you. And indeed, it will stay complicated if all you ever do is watch somebody else do it either on the blackboard or, as in this case, on your television screen or your laptop screen. This is not a spectator sport. You cannot learn it by looking at somebody else do this. You will have to get your hands dirty. So, my advice to you would be, at least try doing this, answering the following questions. If I have a tensor whose components have indices written like this, how would it transform under a coordinate transformation? Also, if you took this tensor and another one, let's say U, with indices C and D both downstairs, and these two C's of course being summed over, how would this overall thing transform? Try to put in the appropriate lambda coefficients, use the properties of the lambda coefficients, and see whether the resulting things make sense to you. Once you do this, you would be in a position to understand most of what is going to come. It is important to actually work it out with your own hands on paper and pen so that the thing really makes sense to you. Even if you think that you have understood exactly whatever I have said so far, I would still urge that you at least try these two simple exercises on your own. But now let us move on from linear transformations of coordinates to what is the topic of the current series, general coordinate transformations. Note that so far what we have said is vectors transform like coordinates. Coordinates transform linearly, vectors transform like that. Covectors also transform linearly but not like the coordinates, in an opposite manner. And notice that even a tensor transformation like this one, in this the new components are really the old components multiplied by some factors and added together. That is also a linear transformation. The coefficients of this linear transformation is built out of the vector and covector transformation coefficients. So this looks pretty complicated, but ultimately what you have is one coefficient for each component and you add them all together. Just a linear combination. So there are linear transformations all around, but all of these really hinge on the fact that the coordinates themselves transform linearly. So everything is fine when you are carrying out a linear coordinate transformation. But what do you do when you have a general nonlinear coordinate transformation where x goes to x prime, which is some function of x? Well, if this is a genuine coordinate transformation, this transformation should be invertible. You should be able to get x back from x prime, but that's about the limit of what you can demand on the nature of this transformation. So saying that the vectors or tensors transform like the coordinates or something similar will not work because the coordinates themselves do not transform linearly. However, despite the fact that the coordinates do not transform linearly, their differentials, infinitesimal changes, do transform linearly. If you look at dx prime mu, how the muth component changes, you can easily rewrite that in this form, del x prime mu del x nu dx nu. Here I have switched over to Greek indices. No real reason except that I will typically use Greek indices more often when talking about nonlinear transformations. Let me point out, however, that in the field of general relativity, there is a standard convention that if we are dealing with, say, four-dimensional space-time, then Greek indices run over 0, 1, 2 and 3. However, again, this is a convention in general relativity that when we want to refer to the spatial components only, like in the case of coordinates, we don't want to refer to the time but only to the spatial coordinates, then we use an index which runs over 1, 2 and 3 only, and these indices are typically taken as Latin indices. But that's just a convention which is used in GR and to some extent in special relativity as well. However, we will not really be following this convention too much in what follows because we are not really going to talk about general relativity explicitly. There will be situations when we talk about general relativity and how the corresponding tensors enter into the picture there, and then I would usually use this particular convention, but in general, the indices can be chosen from any set that you want, as I've already said before. Now, let me point out that here, this del x prime mu del x nu plays the same role that lambda mu nu did in the case of linear transformations. Indeed, when you are sitting at a particular point, and just looking at how the coordinates change when you move from that point, then this quantity, del x prime mu del x nu, is actually something which has to be evaluated at that point. So let's say at the point P, where what I really mean here is that I would calculate these derivatives and plug in the values for the x's at the point P to get the number. So these are actually numbers. In particular, if you had a linear transformation where x prime mu was lambda mu nu x nu, then del x prime mu del x nu would simply be the same as lambda mu nu. Now, how do you check that? This is really rather trivial, but I would really want to emphasize that most of the things that we will do in this series essentially are rather simple if you break them up into tiny bits. So, when you calculate del x prime mu del x nu for this linear transformation, what you are really doing is you are calculating del x nu of lambda mu. Now we have to be careful. I cannot write nu here for the dummy index because I'm already using nu here, which is a free index on this side. So let's say lambda mu rho x rho. Now, for a linear transformation, lambda mu rhos are, of course, just constants, so they can move out of the derivative, and you're left with the derivative of x rho with respect to x nu. Now, the coordinates of a point are all independent. X primes, of course, depend on the x's, but the individual x's don't depend on each other. So del x rho del x nu would vanish unless rho is equal to nu, in which case, of course, this derivative would simply be 1. So this is nothing but delta rho nu, and using the magic of contraction or summation with the delta symbol that we have talked about before, what we get is this is nothing but lambda mu nu, as promised. Now, of course, this was simple enough that you could work it out even without going through the steps, but very often we will be dealing with more complicated calculations where this kind of thing that we have done here, being careful that the dummy indices are not confused with free indices and so on, can really be a very useful thing to learn. So, the important thing is the way in which coordinates transform may be non-linear, but the coordinate differentials transform linearly. The coefficients for those transformations are really numbers, but those numbers, of course, change from point to point in general. For a linear transformation, you get the same bunch of numbers, but those numbers are the same no matter which point you are at. And this is going to be a very, very important consideration later on. Now, vectors under general coordinate transformations would again have d components if you are in a d-dimensional space-time, where the components will be written v upper mu, so mu as a superfix, and mu will run over 0, 1, 2, d minus 1 or 1, 2, 3, d as the case may be. And how do they transform when you carry out a coordinate transformation? The rule is, in this case, the vectors do not mimic coordinates, but rather mimic coordinate differentials. And therefore, the vectors transform linearly. V prime mu changes to del x prime mu del x nu v nu, the same coefficients as that for the coordinate differentials. Once again, let me emphasize that you can actually write this expression from memory or just without remembering anything, more importantly, just by paying attention to the free index and dummy index placement. You have v prime mu on this side, so the prime and the mu, more importantly, is upstairs, so you will have del x prime mu above here, and the other index will have to be a dummy index, and since this nu is upstairs, the nu on this coefficient should be downstairs. Now a nu in the quote-unquote denominator of a derivative also counts as a downstairs index. So this is what we have already said, that this is akin to lambda mu nu. Now, one really major difference which we have already stated a while ago, but let me stress all over again. While the lambda mu nu's for a linear coordinate transformation were identical for all points, del x prime mu del x nu depends on x. Now, if we were dealing with a vector, a single vector which is at a particular point, this issue would not really be very important because del x prime del mu del x nu, these coefficients would have to be evaluated just at that point. So this does not really matter for vectors as such. But what we use very often are not vectors but vector fields. Vectors at different points in space-time. So it's not a single vector but a vector at each point of space or space-time as the case may be. Now this distinction that del x prime mu del x nu changes from point to point. So the transformation depends on which point you are at is crucial for vector fields. And the major reason why this is so important is the following. If you take two vectors at P, let's say capital V and capital W, then the way they transform under coordinate transformations, here we have been careful to indicate that the derivatives here are evaluated at the point P, are just written down here. Of course, they transform identically with the same coefficients. Now, when you linearly combine any two such vectors, say we take V and W and form the combination AV plus BW where A and B are just real numbers, then the muth component of AV plus BW is simply AV mu plus BW mu, and under the coordinate transformation it changes to AV plus BW prime mu, which is of course A B prime mu plus BW prime mu. But using these expressions is easy to see that you can take del x prime mu del x nu at the point P common from this expression and you end up with the transformation law for the linear combination being the same as the transformation law for the vectors, same coefficient, the same del x prime mu del x nu evaluated at the same point P. Of course, here you have the nth component of the linear combination AV plus BW. So, when you linearly combine two vectors at a particular point, you also get a vector at that point. If, on the other hand, V and W had been vectors at different points P and Q respectively, then if you were to change the coordinates, AV plus BW prime mu will be, of course, AV prime mu plus BW prime mu, but now you are in trouble because in AV prime mu, what you are going to get are the following. A del x prime mu del x nu at the point P we knew. What I had written earlier was of course wrong. Plus B del x prime mu del x nu at the point Q times W nu. And in general, this and this are two different numbers. So you cannot take them common out and you do not have a transformation law which says that AV plus BW's muth component can be found out by linearly combining the AV plus BW's muth components or all their components in the original coordinates. So even though vectors at the same point form a vector space, they can be linearly combined together, vectors at different points do not. At this point, I must warn you about something which we have been used to doing from the time when we had learned about vectors. Since high school physics teaches us that a vector is characterized by its magnitude and direction, we are used to shifting vectors around parallel to themselves. That is, as long as we maintain the same magnitude and direction, we tend to think of the vector as the same entity. This, however, is strictly speaking not correct, and this incorrectness becomes a huge issue when we are dealing with non-trivial geometric situations. We will see a lot more of why this is a problem later on. Let me just point out that even in mechanics, especially in rigid body mechanics, we talk about a vector like a force, and we often think of translating it along its own line of action and say that all these forces, as long as they are moving them along the same line, has exactly the same effect. But this is true only in rigid body dynamics, and that too only as long as the point of application of a force stays within the rigid body. Now that is a very special result which follows from the fact that the motion of a rigid body is dictated by just the net force and the net torque acting on it. So shifting a force parallel to its line of action keeps both the net force and the net torque the same and does not affect the motion of the rigid body. On the other hand, applying the force at different points may really have very different effects if the body is not rigid. Push a blob of clay here and push it here with the same force, you will have entirely different effects. So, this warning that I have for you, that you should not really think of moving a vector around parallel to itself. Rather, you should get used to treating a vector as something which is stuck to a given point. Actually, something we should have learned in physics as well. It's just that in elementary physics, we often talk of applications where this doesn't really make much of a difference. And so we have been blissfully unaware of the troubles which we can face if we were to do this. One very important consequence of this is you cannot really compare vectors at different places unless you have some additional structure in mind. So, for example, when you're differentiating a vector field, what you would do is compare the value of that vector field, which is a vector at a particular point, with the corresponding value at a neighboring point. And this comparison is fraught with danger unless you have a notion of how to transport a vector from one point to another without quote-unquote changing it. Now, we will have a lot more to say about this, how to transport a vector from one point to another, and hence how to compare two vectors at two different places later on. After all, differentiating a vector field is a very important operation in physics, and we want to be able to do it. But for that, we will need a lot more structure. We will, of course, discuss this in a later lecture in some detail. Now, with this word of warning about vectors, let us turn to covectors. Covectors, of course, like in the case for linear transformations, should transform oppositely. And what is, of course, important is that even now, they give scalars when acting linearly on vectors. Now, one example of a covector that comes about very naturally, especially in physics, is the following. We start with a scalar field phi, then d phi obviously is a scalar, under x mu going to x prime mu, which is a function of x, phi of x goes to phi prime of x prime. And the important thing about a scalar field is phi prime at x prime is equal to phi of x. Note that x prime and x are coordinates of the same physical point. So what we are saying is that the scalar field changes as a function of its arguments, but has the same value at the same physical point. Now if this happens, of course the change in the scalar field between two neighboring points also stays the same. So d phi, the change in the scalar field, goes over to d phi prime, which has to be the same as d phi, which is exactly what we meant when we said d phi is obviously a scalar. Now, calculus tells us that d phi, seen as a function of x1, x2, x3 up to xg, is simply del phi del x mu times dx mu, of course sum over all possible values which the index mu can take. This is nothing but formula for the total differential of a function. So if you just think of the coefficients here, del phi del x mu, as mu runs from 1 to d or 0 to d minus 1, these must form components of a covector. Dx mu's are obviously vectors. They, after all, are prototypes of all vectors. And del phi del x mu's act linearly on dx mu's to produce a scalar. How do the covector components transform? We can of course see under the coordinate transformation, del phi del x mu goes over to del phi prime del x prime mu. Now phi prime is a function of x prime which is the same as phi of x, and of course phi of x is ultimately a function of x prime through this change of coordinates. In order to figure this out, we could replace these derivatives with respect to the new variables by derivatives of phi with respect to the old variables, remembering of course to use a chain rule for partial derivatives. So del phi prime del x prime mu is given by del x nu del x prime mu del phi del x nu. And since del phi del x nu's were my original components for the covector that we are talking about here, del phi prime del x primes are the new ones. This is how you relate, at least for this particular covector, the new components with the old components. And you can generalize this to figure out what the general rule for a covector transformation would be. For a general covector V mu, where mu runs either from 0, 1 to d minus 1 or from 1, 2 up to d, we have the following transformation rule, which is just modeled on the way in which this object, the gradient of phi, transforms. So for a general covector, the transformation rule will be V mu goes over to V prime mu, which is del x nu del x prime mu times V nu. Note once again that for a covector at a point, these derivatives are actually evaluated at that particular point P, and therefore these would just be numbers. Of course, when we talk of a covector field, we would want to know how covectors at different points also transform, and there these coefficients would in general depend on which point you are at. And it's obvious, just like del x prime mu del x nu, the factor which tells us how vector components transform, was akin to lambda mu nu, this lambda mu nu, the vector transformation coefficient. For in the linear transformation case, the coefficients del x nu del x prime mu would also be analogous to the covector transformation coefficients, lambda, lower mu, upper mu. Let us quickly see why that is true. If we were to calculate del x prime mu del x nu times del x nu del x prime lambda, of course summed over nu, then this expression, according to the chain rule of partial derivatives, is nothing but del x prime mu del x prime lambda, and since all x primes are also mutually independent, this must be the Kronecker delta mu lambda. So, if we were to consider this del x prime mu del x nu, the coefficient that sits in front of vector components, as a mu nuth element of a matrix L, then del x nu del x prime lambda must be the new lambdath entry of L inverse, or the lambda nuth entry of L transpose inverse. This is exactly the way in which the two lambdas, remember, for linear transformations, lambda mu nu was the mu nuth element of L, and lambda lower mu upper nu was the mu nuth element of L transpose inverse. The partial derivatives automatically obey this condition, and therefore the moment you take a vector and a covector and make one act on the other and form the entry like V mu W mu, that is V upper 1 W lower 1 plus V upper 2 W lower 2 all the way up to V d W d, then this thing has to be a scalar. A quick check of whether that's true, although frankly This should be obvious from what we have said so far. V upper mu W lower mu under a coordinate transformation becomes V prime mu W prime mu. V prime mu is del x prime mu del x nu V nu, and of course we have to change the dummy index here. W prime mu has a del x prime mu of x lambda W lambda. These can be moved around, and if you bring this to the front here, you can easily see that this is nothing but del x lambda del x nu, and therefore that's delta lambda nu V nu W lambda, and therefore this V prime mu W prime mu is the same as V nu W nu. That's the same, of course, as V mu W mu, and therefore this quantity does not change when you do a general coordinate transformation. Now, how would V lower mu W lower nu transform? Notice that unlike this, in which there is really no index, the index that you see here is a dummy index. So this has no free indices, and you cannot talk about its components. This is just one single number. But unlike that, V lower mu W lower nu, this quantity, actually has two indices mu and nu. And so this is really not one number, but a collection of d squared numbers. Now how would this transform when you were to do a coordinate transformation? That's pretty easy. Both the V lower mu and the W lower nu would transform to V prime mu W prime nu. V prime mu, according to the covector transformation rule, is simply del x lambda del x prime mu V lambda. Once again, remember, just looking at the positioning of this free index should be enough for you to be able to write the whole thing. And then W prime nu is del x prime nu of x sigma times W sigma. And by putting the coefficients together, we get this transformation rule. V prime mu W prime nu is a linear combination of the old components V lambda W sigma, but the coefficients are del x lambda del x prime mu del x sigma del x prime nu. Now this is exactly the way in which a 0-2 tensor is going to transform. A 0-2 tensor in general will have two indices mu and nu, and when you do a coordinate transformation, T prime mu nu will be connected to T lambda sigma. Note the similarity with this, with these coefficients. This is of course a single number formed by multiplying two numbers. Each of these are covector transformation coefficients, del x lambda del x prime mu del x sigma del x prime nu. Just to remind you that in the linear case, what you would have obtained here would be something like T prime mu nu is lambda mu A, lambda nu B, T A B. Of course, I have called the dummy indices A and B for this, whereas there were lambda and sigma here, but that of course doesn't really make a difference, these being dummy indices. Well, it's very easy to see that if you had started with, say, an object like V mu W nu, you would have ended up with something which transforms in a different way. In fact, what we are talking about here is more like V upper mu W lower nu. This goes like T mu nu, its transformation. This is something I can write down without even worrying about anything else. The upper index mu here says you will have a del x prime mu here. The lower index nu tells you will have a del x prime nu in the other factor. And then you need to differentiate this or differentiating something here. That is, you need to complete the derivative with the old coordinates. Now, what you call these indices is up to you, but if you put a lambda down here, you have to have a lambda up here. Put a sigma up here, you have to have a sigma down there. Similarly, if you had a 2-0 tensor with two upper indices, you will have a del x prime mu and del x prime nu in both factors. Del x prime mu will be with respect to x lambda, or x of anything. Del x prime nu will be del x something. But once again, you have to be careful. This lambda has to match this lambda, this sigma has to match this sigma. So of course, you could equally well have written del x prime mu del x a, del x prime nu del x b, TAB. If you just keep the positioning of the free indices straight and remember about the contraction rule that you have to have an upstairs and a downstairs index, you should be able to reconstruct any tensor transformation rule. We can go on to talk about the way in which more complicated combinations of tensors transform. For example, if you had a rank 2-0 tensor here, R mu nu, a rank 0-2 tensor, and another rank 2-0 tensor, and we were to multiply all their components together, you would have an object which has essentially 6 indices: mu, nu, lambda, sigma, rho, and phi. Of course, this means that this is not really a single number. Since all these indices can take d values, this is really a collection of d to the power 6 numbers put together. How does this transform? Well, I've written this down here, and I've used different colors for each different piece so that you can easily see where every term is coming from. The R becomes R prime mu nu, which is of course the same as del x prime mu del x a, del x prime nu del x b, RAB. The S becomes S prime lambda sigma, orange on this side. So del x prime lambda del x prime sigma of xc and xg respectively, SC is SCD. Here I am mixing deliberately the Greek and the Latin indices simply to ensure that we do not have any conflict of two different dummy indices matching by accident. Similarly, T prime rho phi will be del x prime rho del x e del x prime phi del x f times TEF. And now if I move all these coefficients to the front, I see that R prime mu nu S prime lambda sigma T prime rho phi will be linear combinations of the old components RAB, SCD, TEF with a single coefficient which is the product of 6 transformation factors. 2 of these are covector transformation factors, the other 4 are vector transformation factors. Upper indices correspond to vector transformation factors, lower indices correspond to covector transformation factors. And this should give us enough practice in understanding how a general tensor would transform. Let me just remind you that if the coordinates were to undergo a linear coordinate transformation, a tensorial object like this, T upper ij lower kl upper mn, would transform in this fashion, where each of the upper indices ij, mn will have lambda factors corresponding to vector transformations, and each of the lower indices will have the other lambda factors corresponding to covector transformations. And all of these 6 factors will multiply together to give a single coefficient for T, A, B, C, D, E, F. Let me stress once again, this is really not one single equation, since ij, kl, mn can take d to the power 6 values in all, and this equation is valid for every one of them. This is really d to the power 6 equations written in one, and on the right hand side of each of these equations, you really have d to the power 6 terms, because the dummy indices A, B, C, D, E, F can take d values each. Now this is for the linear coordinate transformation. For a general coordinate transformation, this is what will happen. Very similar to the linear coordinate transformation case, the upper indices will lead to vector transformation coefficients. The upper index mu will give rise to del x prime mu del x a, and of course the corresponding index for the old component of t will be a. Then you will have del x prime nu del x b, but for the lower indices lambda and sigma you will have del x c del x prime lambda del x d del x prime sigma, again del x prime rho del x c del x prime sigma del x f, multiplied by t, a, b, c, d, e, f, and summed up completely. Once again, let me emphasize that this is not a spectator sport. So if you want to get fully conversant with these things, it's best to take pen and paper and write down a few such relations yourselves. In the next lecture, we will continue with various algebraic properties which follow from the tensor transformation rules. Most of these will be similar to what we did for linear transformations, but with some changes. Then the major changes will come in whenever we want to differentiate vector fields or tensor fields or covector fields. This is simply because while you can combine linearly vectors, covectors, tensors of the same kind at a given point, you cannot really combine directly these entities at different points. And differentiation requires you to subtract an object at one point from another object of the same kind at a different point. We will of course see how to handle these things in some detail in later lectures. Bye for today.